Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 20 in our Paper 2 series, and it is on the advanced information for both foundation chemistry and higher tier chemistry. What we're going to be looking at in this booster is crude oil. So when we talk about crude oil, first and foremost, we are talking about a fossil fuel. It's a fossil fuel because it forms the remains of living things that lived millions of years ago. Those living things died, became buried deep under the seabed, and eventually turned into crude oil over millions of years. Because crude oil takes millions of years to form, we refer to it as a non-renewable resource. That just means that we are using it faster than it's being made. So it's going to run out. One word that they do sometimes use associated with this is the word finite. Finite just means we've got a limited amount available. We need to be able to explain how we separate crude oil into the individual useful fractions. So first thing to know is that it is done in the process of fractional distillation, which uses this thing here called a fractionating column. So they can ask you the name, they can ask you obviously the piece of equipment, and they can also ask you to explain how this works and to just fill in blanks on the actual fractions and where they come out. So down here where we can see the names of the individual fractions, you need to know them in sequence, I'm afraid. There's no kind of easy way around this one, it's just a learning exercise. So LPG at the top, then petrol, paraffin, diesel, heating oil, fuel oil, and then bitumen at the bottom. So how does fractional distillation of crude oil work? Well, our hydrocarbons have different boiling points because each of those hydrocarbons has a different length molecule. The longer the molecule, the stronger the intermolecular forces, and therefore the higher the boiling point. Our fractionating column itself has what we refer to as a temperature gradient. By that we mean it's hotter at the bottom and cooler at the top. So what we actually find is, as we send in our crude oil vapour at the bottom where it's very hot, then the vapours rise, but as they obviously go beyond their boiling point, so as it drops beneath that, then what's going to happen is it's going to condense, and then we can just run off those individual fractions. Key thing to remember on that is hydrocarbons have different boiling points based on the length of the molecule. So longer molecules, stronger intermolecular forces, higher boiling points, and we've got this temperature gradient within the fractionating column itself. What that means is that the hydrocarbons with the highest boiling point are going to leave at the bottom. That's our bitumen. Whereas the hydrocarbons with the lowest boiling point are going to leave at the very top, LPG, and that is a gas. You may question why it is that when we're heating things up to like 350 degrees Celsius, how do these molecules stay together? Well, the atoms within the hydrocarbon molecules are joined together by these covalent bonds, and covalent bonds are strong bonds. So what we do know is that those strong covalent bonds are actually going to be much stronger than the intermolecular forces. Now, intermolecular means between molecules. So when we're thinking about it, if we've got our individual little hydrocarbons, then there are forces between those molecules. So each of these hydrocarbon molecules is going to have forces between them. That's the intermolecular force. They're weaker than these covalent bonds within the molecule. So as a result, when we heat it up, the intermolecular forces break, but the covalent bonds remain. One of the key things that we find in terms of our fractional distillation process of crude oil is that we don't get the fractions in the right proportions for what we actually need. So we end up with way more of these much longer hydrocarbons than we need, and not enough of the smaller ones. So what we do is we use a process called cracking. Now, cracking is going to convert large alkane molecules into the smaller, more useful hydrocarbons. In order to carry it out, we need a catalyst and a high temperature. And to give you an example of what we mean, here's an example. So we start off with octane, which is an 8-carbon alkane. And then when we heat it up in the presence of our catalyst, it's going to split into hexane, 6 carbons, and ethene, 2 carbons. So we've broken up that larger alkane molecule into a smaller alkane and an alkene. Because we do this with the fractions we get from fractional distillation of crude oil, that means we can match supply to demand. Because through this process of cracking, we break the covalent bonds between the atoms to make those smaller fractions that we need. One of the reasons we do seem to have this surplus of the larger alkanes is because they're not overly useful. They're not great at flowing, they don't really flow easily, and in terms of trying to ignite them so we could burn them as a fuel, again, they're really hard to ignite. So for a lot of our uses, the large alkanes aren't good. Therefore, if we can split them up into those smaller ones, then they are easier to ignite, they flow more easily, and that makes them way more useful. If there are bits we've gone through in today's booster you'd like to see in more detail, you could use the C6 playlist on the channel, your revision guides, classwork notes, and as always I do recommend having a look at least a couple of those past exam papers before your exam. Then don't forget to join us again tomorrow for our next Chemistry Daily Booster.